Well, hi everyone. My name is Ellen Fireman, and this is Stat 200. So I want to welcome you all here today. And what we're going to do today is go over the syllabus, have a brief introduction to the structure of this course, which is a joint online in-person class, abbreviated as cool. It is cool. It's incredibly cool because you'll have all the resources of the people here in person. You're like the live audience, and then there's an audience at home, and both of you have access to all resources for the course. So what does this cool stand for right here? It stands for the Coordinated Online Learning System, which seamlessly integrates online and in-person classes. And we're actually conducting a study on which works better for which students, which we'll talk about later in the hour, because our very first two chapters in the notebook, in our textbook, is about how to design a good study. So we'll see how good we're doing with that. All right, so now, what I'd like to do is just tell you, first of all, it's a little confusing because there are 3 websites for this course. Now this one, which you can just get to by Googling Stat 200, is publicly available, has all the information that you need about the course. In fact, this calendar is super useful for it's essential for the online people because this is where all the lectures will appear. So if you're watching this and missed this class, like some of you are going to miss this class some days, you just go right to the day of the class, and a few hours later this is going to be a link, because we are Tuesday, January 15th. It will be a link to exactly what we're doing right now. And so you can see the whole course in a glance. Now I just have it updated for the first 2 months, but basically you'll see when the homework is due every Monday and Wednesday at 11:59 p.m. on another website. This is our second website, Lon Kappa. This is where you turn in all your work. If you get graded on something besides an exam, if you get graded on homework or bonus work or all this bonus work here, coded in blue, always do it Fridays at 11:59 p.m. And your homework, your required work, always do Mondays and Wednesdays at 11:59, coded in red. So what I'd love to do is just have a course that has one calendar, one place where you just click and go, bingo, I see the lectures. If I missed a lecture, if I want to hear, this should be links to exactly what you're doing, but it doesn't work this way because these homeworks are behind protected, password, so you can't just link to them. You have to go to the site. So for all work that you see, whether it's red or blue on this calendar, anything you're going to turn in, you're going to be going to our homework site, which I'll talk about later, where your homework is immediately graded. So we'll talk about that later. First, I just want to get through the syllabus so I don't forget anything. I will also put when your exams are, and there is a link to our exam schedule. We can look at that right now. And this course only has 3 exams, 2 midterms, and a final that really is a midterm, a third midterm. They're all 90 minutes, and they all are non-cumulative. So, for example, your first exam just covers the first 18 chapters, the next will cover the next chapters we do, and then the final will be the last third of the course. All right. And your exams, because I want to, other sections are also taking this course, and they only meet for an hour. I want everybody to have the full hour and a half. So we're going to meet at night Wednesdays, February 20th and April 3rd, with conflicts at 4:30 the same day. So if you can't make either of those 2 for some reason, please contact me right away so we can set something else up if you know in advance. If you don't know, if you just missed the exam for illness, well, if you miss any exam and have written proof, then what we're going to do is give you a makeup during the final exam time. Because the final exam is only 90 minutes, but you're allowed 3 hours, twice that long. So it will just be the second, you'll just get your makeup exam during that time. That's the simplest for everybody. So that's what will happen if you miss an exam, for any reason. As long as it's an excused absence, you can't just blow off an exam. Okay? Does that make sense? All right. Now, let's go through the syllabus to make sure that I don't skip anything, and please feel free to interrupt me whenever, I hope this is, can you hear me? Does this sound like it's on? Okay. Feel free to interrupt me at any time with questions. Just raise your hand. All right. So here we are. You're in the, people in class are in the L1, people online are being taught by me, but there's also 5 other sections using the same exact course. All right, so here's our course webpage that we're looking at now, and here's this required textbook, the Stat 200 Incomplete Notes. Let me get a copy of that so you can all see what it looks like. It's a light blue notebook that functions both as a workbook and a textbook. It's basically what we're going to be completing together as soon as we finish going through the syllabus. So let me show you what it looks like. Here, I should put it on the screen so people online can see this too. We're going to be working on it together using this document camera, so let's make sure that works and everybody can see this book. Yeah, so it looks like this, and it has all the explanations, a lot of problems, and we fill it in together. And we fill this out together. And this is the best pedagogical tool that I've come across to teach both online and in-person classes. Even the small sections like it, it just saves so much time and makes the learning more interactive. So many studies have shown, particularly with math classes, if you actually write the problems, work out the problems with a pen or a pencil, that you learn better and remember better. You often feel like you're learning when you're watching a lecture, but when you go home to do some problems, you don't remember it. So this reinforces the memory. Okay, so let's go back to the syllabus and continue. I think it's $35, and if you don't, bring it to every class. And if you're home watching this, it will make watching it so much less passive and more, it's even more important for the online people, because your eyes will just glaze over listening to, 80 minutes of me just lecturing without even seeing me. You just see the screen. So it's a huge plus for online people and for in-person people too. Okay, so then the only other thing is you need a calculator for the exams. And so I would love for you to use a graphing calculator. I like them much better myself, but people have been cheating on them by programming them and so forth. So you can use any non-programmable calculator, and the one we recommend is, there's a link to it here. Okay, so what else? So class time, obviously you know that. The online people are welcome to come to this class whenever they want, and you guys are welcome to watch the videos whenever you want, even if you're in class. I know you can't pay attention for 80 minutes straight. Who can? Barely pay attention for 10 minutes straight. So you're going to miss stuff. When you get to the homework, you're going to say, whoa, what was that about? Maybe I need further explanation. Even if you have it in your notes, you might want to see how it was explained. You just go to the calendar, and you can watch the lecture videos too. So just a few hours after class. So office hours. We have office hours 3 times a week in this building, and on the 3rd floor of that building where my office is. Technical issues. Okay, we use a lot of technology in this class. So if you have any technical issues, then this is our tech doctor. He's amazing, and he will solve them for you. So please email him. He's will solve them way faster than I would be able to. So you can CC me on it, but email this guy, Dr. Yucktung Liu. All right, his office is right in the same place where the office hours are, right next to my office. All right, now homework schedule. Okay, lots of homework for this class, and it's worth 25% of your grade. Each exam, including the final, is 25%. So it's as much as the final. Now, so here's when it's due, every Monday and Wednesday starting this coming Monday, and on Lon Kappa. So maybe it's time now to look at Lon Kappa. You can click there, but I have it open right here. And oh, this looks kind of messy. It's not the most user-friendly or prettiest website because it's free. So people aren't buying it. So there's not as much motivation to make it look really pretty, but you're not paying anything for it. In all the other ones that I looked at, well, there's some that you wouldn't be paying for, but this has tremendous capabilities. So I'm going to walk you through it so it makes it a little bit easier. So you go, if it looks a mess, just click. What you need to know is on the contents. So click on contents right there. Let's do it from your point of view because you're not going to see all this hidden stuff, and it'll look much nicer. So let's pretend I'm a student. Okay, so let me just put in something here. All right. So this is, and let's see what it looks like. All right, so there's two things. There's the required homework and the bonus. All right, so this Friday, you have some bonus work due, so you might as well just try it right now. Let's look at it and just look at what it looks like. So there's these pre-lectures that you can do before the lectures. They're due at the end of the week the lectures were given, but they open up earlier. So you're free to do them afterwards, but it makes more sense to do them first. So here's the Chapter 1 pre-lecture, which we're going to be covering today. And there's a lot of clicking in Lon Kappa. So here we click, and here we click again. And this will tell you when it's due, but you know that from the calendar already, and we can look at it. So these pre-lectures are short videos, very simple, basic videos with short answers. And so let's say we watch the video, and of course I want you to watch the video, and now you answer these questions. So let's just say, just to show you how it works, let's say we just answered a question. I'm not even looking, I'm going to get it wrong, probably. Yes. Okay, so it says incorrect. So that told me that I used up one of my tries. This tells you how many tries you have. You don't lose any credit for using up your tries. It's not like the problem's worth less with each additional try. It's worth the same. But obviously, it's best to think about it first, so you get that, because you'll learn more, and try to get the right answer on the first try. So that's the idea. And then you can always, if you have a question, you could post something here. Like, I don't understand this, whatever. And you can post it as an anonymous person, but I'll still see who you are, but no one else will. So don't say this is bullshit or something like that, because it won't be, I'll know who you are. Okay? I'm just warning you. And it's not helpful. You can, valid criticism's fine. Okay. Now, so then you can move on after you do that one. You can move on to the next one. This is on Chapter 2, and etc. Okay? Any questions on that? So every Friday you're going to have some bonus work due, so just know to expect it and know to go to the pre-lectures. Now, let's go back to the contents, and I'll show you something else that's really cool about this course. Is so much stuff is opened. So if I go, what do if I do it? If I do that, let's see what it looks like. Okay, so if I do this again, go to the bonus, the lectures, and I want to go to the surveys. That's what I want to show you. Okay, so the first Friday of every month, and we're considering this Friday the first one of class, you have a survey due. And these are really fun because we use these, they're anonymous. You get credit for them, but there's no way for me to tell who submitted what answers. So you'll get credit if you answer all the questions, okay? And this is just a great way to analyze data. Statistics can be about anything, right? And it's like, it can be really boring if you're not interested in the question, right? But if you are, well then it's fun. And so I figure most people are interested in themselves, so a lot of what we do in this class a lot of the examples will be our own data. Just to make it more like we're real scientists, real data scientists, real problem solvers, because we'll know more about that data than anybody else, and we'll be able to ask interesting questions without having to jump through all sorts of preliminary hoops and figure out where the data come from, why, how is it worded, blah, 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 blah. We know all that intuitive. You know, we took the survey, so we're miles ahead of using other outside data sets so that we can really dive in and look at, hey, what's going on? What are the possible, can we conclude causation here, between these correlations? What are the possible, confounders? We'll learn about that today, but it'll make it much more fun. So that's the idea. So answer honestly, because that's more fun. Plus, I gather information about the class. All right, any questions on that? So obviously it's not right or wrong, but try to answer honestly. I think let's go back to the syllabus so we don't get off track too much. Here's your grading. I mentioned that before. Everything's worth 25%. Now what are these bonus points? These bonus points are scaled. It's not like you're adding. If you earn 5 bonus points, that doesn't mean 5% is added to your grade. It's added by this formula here, which is a scaled formula that can't go over 100%. So for example, if you did 100%, all 100 points, and let's say you got a 75% on the required work, this is the formula for it. So it would raise, in this case, it would raise you up to an 80 from a 75. But as you could see, if you put 100 in here on the required work, you'd have 125 over 125. So it's a scaled system helping those who don't do as well on the required work, particularly on the exams, to boost their grade. And it's not busy work, it's work that will benefit everybody. It's fun or helpful, helps you understand stuff. So but of course, if you don't want to do it, you don't have to. You can still get 100% without it. So what do you get bonus points for? Those pre-lecture bonus problems I just saw you. Turning in a notebook, a completed notebook at the end of the semester, at the final will earn you 30 bonus points. We'll check it at the final. Those people who are taking this course in China or somewhere where you can't get to most of the online people will be taking the exam on campus because you're nearby or here. But there's some people who can't get here, and you can turn your completed notebook. You're probably wondering, how would I turn my completed notebook in? Well, if you have any question, just go to, where is it? FAQs, and it's probably on here. So let's look for off-campus students. Yes, so it's right here. So if you have any question before you email, it's so much easier just to go on this site. And if it's not here and you think, then of course email me, and if it's one that I think a lot of people are going to ask, I'll put it on here. So back to the syllabus, and back to the bonus points. All right, so everybody has this opportunity to turn in the completed notebook. More explicit directions will be given, when it's closer to turning it in. So then the surveys you just saw, and then there's these R bonus point problems. Everybody asks me, is R taught in this course? Well, we do have these R bonus problems. You don't have to do them. There'll be 5 or more of them, and they count as bonus. So what do I think about whether to teach R or not? Let's go to our home, which gives the course philosophy here, and what the goal of the course is, etc. And there's one of the main goals is learning to use statistical software because it is so important. But we want to learn it both to help us understand what the statistical methods are doing and to do the calculations for us. So to do that, we do have this amazing simple point-and-click data program that you can get to. We're going to be using it a lot, and you get to it right here. And that's where we're going to be loading our own data and analyzing it. And it lets you compare the same data sets with a variety of methods to see how the results they give differ and why. That's what we're going to be doing a lot of in this course. We're not going to just show you one way to... Statistics is a toolbox, and you have to understand which tools are appropriate for which problems you want to solve and why. And so this enables us to do that. So we can get a feel for which of the methods, which are all usually just approximations to the real world, right? I mean, statistics is using math to understand the real world. Similar to physics uses math to understand the physical world. Well, statistics uses math to understand the everyday world we live in, and so it's messy. I mean, that world is messy. Math is beautifully pure, abstract, and combining those two is, they don't fit well, right? And so you have to figure out which tools work approximately the best. That's what statistics is. So some of them work better, and some, which situations works better to analyze the data. So we're going to use a variety of tools, both theoretical ones based on theoretical assumptions called parametric tools and non-parametric ones without those assumptions. So we focus on understanding the underlying concepts behind the methods so you can choose your methods wisely. That is what this course is about. And people tell me over and over and over again how useful it is when they get to the higher level courses and you get things are more complicated. And some of those underlying concepts are masked or developed to such an complicated extent that it's hard to go back and find the basic building blocks. So once you do understand those needed statistics, though, using applied calculations usually requires more flexible software than our data program. And that's what R is amazing for, because you can basically program it to do a lot of different things that you can't do through ordinary SAS or SPSS or whatever data program you have. It's computer program, it's statistical computing, so you can do whatever you want. So we have bonus exercises on using the R statistical language to acquire basic familiarity. Now, for those of you, and I asked on the first survey, have you taken computer programming before? We do offer this free non-credit R course. That's an amazing course, but it's really hard. In my experience, it's been difficult to teach R as a first programming language. So if you have experience with something else, this would be much more likely to benefit you, but you're free to look at it. It's a full course, and we used to offer it in conjunction with the old Stat 200, which was a more advanced course. This one is now a beginning course. By the way, you need no prior statistical courses to be in this course. So this is too much cognitive overload. If you're just coming into stats and you don't have any programming experience, but if you already have some if you already have some stats and you already have some programming experiences, I think this is an amazing course. And it's free. Okay, so that's the deal on R. Now what else? Let's go back and make sure we did not skip anything, and then we can start the first lecture. Okay. Contents of the course. That's important. The course, look what it covers. This is huge. We're going to start with the study design today. Then we're just going to do the usual descriptive stats, summarizing the data that you have. And then we're going to look at statistical inference, statistics for random variables. So using the data at hand to predict, making statistical inferences about a wider population. And then we're going to look at significance tests to see if some difference we see between, for example, a treatment and a control group, some difference in their responses is big enough to make it likely that it wasn't due to chance, that it's due to some real effect. Okay? I mean, is your difference some difference you see due to random variation, or is it due to some particular cause? That is the crux of statistics, random variation, studying it. Let's see what else. Then, and of course, in this statistics for random, for right up here, we're also going to look at probability. I forgot probability is key because all statistical methods are based on probability models. We're trying to see how things vary, right? So we have to see what the underlying probability model is. In this class, we make that explicit with simple box models. So, all right, let's go ahead. Where are we? So then this experimental power, what types of errors? There's these two types of errors. How much power does your significance test have? That means the power to detect an effect as large as the one that you want to detect. How big a sample do you need to be able to see if some difference between two groups is significant? And then we're looking at multiple groups here, ANOVA for comparing more than two group means. And then we're looking at regression, correlation and regression, and then inference for regression, and multiple regression, and then these re-randomization methods. These are randomizations tests to calculate these p-values instead of the significance test. And then what else are we going to do? This transforming variables, fitting a linear model to nonlinear data. Logistic regression, where you have a predictor that's just yes, no, like life or death. And then these non-parametric stats that are just really cool, that transforms data into ranks that are close to, make it simpler to analyze. So that's the goal, and that's a huge amount of stuff. So we better get started, if there aren't any questions. Any questions? Okay, so let's go to the notebook then and the document camera. And just a show of hands, how many people have already taken Stat 100 here at this campus? Okay, so this part's going to be easy for you. Super, super easy because you've already seen it. So don't get bored. There's a lot of you in here. But this is going to look super familiar to you because it's the same as what you've already seen. But after about the first few weeks, it's not going to be the same. So, also it goes a little bit faster. So, all right. So here we are on page, let's make sure this is focused good, and that everybody can see this. Now, if you don't have your book yet, don't worry. Okay. So, we do these studies to find out, obviously, if a treatment has some kind of effect, right? The treatment could be a drug, an advertising campaign, an educational method. Right now, you are involved in a statistical study to see whether online learning, what the learning outcomes are between in-class learning and online learning. Is there a difference? Do people learn better one way or the other? If so, we're trying to identify which groups learn better which way or the other. Okay, so you are involved right now in a study. So, okay. So now, if the researcher decides who gets the treatment, and the investigation is called an experiment. So you can call one the treatment. We could call like the online learning the treatment because it's newer. We have a pretty good idea of how people learn in class already. We've been doing it for years. And we can say, okay, we're comparing this. It doesn't really matter which one you call the treatment. One is the treatment and one is the control group. We have a comparison here. We're comparing online learning to in-person learning. Okay? Now, so if I decide who's in which group, then it's an experiment. But what if I don't decide? What if you guys decide, or if I just study the effects but I have no part in deciding who takes which course or who gets in treatment and control, then it's called an observational study. So which one is this experiment? Is it an experiment? Did I decide whether you're in person or online? Raise your hand if you think it's an experiment. Obviously not. You guys decided. So this is more or less an observational study. But I set it up, but you guys did decide to be, you registered, and you registered for one class or the other for whatever reason, right? So I'm just observing how well you did. I didn't assign you, okay? So both experiments and observational studies compare the responses of those getting the treatment to those not getting the treatment. This is really important. This is the comparison group. A control group is really just a control group. It's just a comparison group. That's all it is. Because we want to compare two groups, right? If we don't have a comparison group, how can we know whether something works? You have to compare two things. All right? So, so an experiment means that the researcher decides how to divide the subjects into treatment and control, and there's two basic ways that this can be done. One of the ways is they can do it non-randomly, picking out the people who should be in each group, or randomly, letting some chance objective procedure decide who's in which group. Now, these observational studies, the researcher has no power over assignment into treatment and control. Sometimes it's subjects themselves, or sometimes it's simply fate who determines, who gets which treatment. For example, if we wanted to study whether firstborn, there's a lot of studies about whether firstborn students achieve more academic success. Well, we have no control over that. That's just fate, if you're firstborn or secondborn or thirdborn. But we certainly want to study that. Anything that's harmful, we can't assign people to treatment or control. Why can't I assign you to treatment or control? Because the university won't let me yet. And because students don't want it. They want to pick themselves. They might not want to be guinea pigs. They might think they know which one they want. So there's a lot of obstacles to doing an experiment, as opposed to, usually the observational studies are done out of necessity. Okay? So the ideal study is what? What is our goal here? Let's think about it. We want to compare, we want to know if some treatment works. So ideally, what we want is to have the same exact people in both groups. Like if you were taking this on here in person, right, and your clone is taking it online. So you start off exactly the same, exactly. And then the only difference that happens is the online is given to them and the in-person is given to you. You start. Then, at the end of the course, and I can see who did better, we know if there's any difference between the two, it had to be due to the treatment, because everything else was exactly balanced and the same. You're the same people at the start of the study. So before the treatment, we want the treatment and control group to be as alike as possible. That is the goal. So here's the treatment group, and here's the control. And not only on the characteristics we think might be important, like whether you got A's in previous math courses, your ACT score, no, on everything. Same people. Well, obviously we can't do that, but we want them as like as possible. That is our goal. Right here. Let me get a highlighter here. Treatment and control group as alike as possible. Why? Because then, this is before the treatment. Everything's the same. Then after the treatment, what are we going to do? After the treatment, we're going to compare the response compare the responses. This is the treatment group, and this is the control group. In our example, the response might be your overall score at the end of the course. Okay, your grade overall. And to see now, we compare the responses of the two groups. Compare responses of two groups. to see if there's any difference. Now, if they weren't balanced to begin with, and we can't even measure the imbalance because we don't even know all the identifiable relevant characteristics that we're trying, they're not balanced, then how can we measure, how can we figure out this? So the goal is to start them off as alike as possible, and then to see if there's a difference at the end. And if there is, it had to be due to the treatment because everything else was the same. Everything else was balanced. Understand? Does you get the idea? Okay. So how do we make them as alike as possible? That is the key. So let's go to it. Really, I loved looking at drug tests, medical studies, because they're very clear and they use a lot of these randomized ideal experiment. I shouldn't tell you what's ideal, but they do a lot of these clinical trials where they give the drug to one group and not to the other. Okay, so let's say a new drug designed to help students learn stats was proven to be safe, and the university decided to conduct a study to test its effectiveness in this class. Okay? Or these days, a new chip that could be implanted in your brain, right? And then they could just scan your head at the end. Like your head was a cantaloupe and put it across a conveyor belt. Did they learn it? Did they not? That's the future, right? Okay, but anyway, we're talking about a drug here. And what's the best way to make the treatment and control group as alike as possible? Remember, that is our goal. And you know why now, right? So let's just write that, because that you have to keep in mind. For the main goal is what? That we should be thinking of in designing any study is to make the treatment and control groups as alike as we can. Okay, so what's the best way to do this? Well, there's lots of different ways to proceed. We could use historical controls. We could give everyone in the class the drug and use last semester's class as control. That's one way we could do it. Now, what's the problem with that? The treatment and control group are going to be necessarily different, right? This is very easy to do. That's why people do this one, and it's not, don't throw it out. I mean, we want to see these results, but they're problematic. This is very easy to do, right? But the treatment and control groups are bound to be different. They have to be different because past conditions are different than present ones. Okay, how about if we let the students decide whether to be in the treatment or the control group? Well, that's what you guys want. That's why I can't do a randomized, I can't assign you, I can't do an experiment, because it would make students unhappy. But we're never going to figure out which works, really, unless that happens. So if students understand statistics better, my goal is they'd volunteer for a randomized experiment, maybe, or we could give them some incentive to do that. I mean, we have to admit that we really don't know yet. The problem is that most students think that they know which is better for them, but maybe we're never really going to find out unless we do a randomized experiment. So the subjects will be happy. They like, it's wonderful to do after you know which works, then allow people freedom. I'm all for that, totally, with full knowledge. Then you could have full knowledge, the studies published and everything, you know, and then you decide. I'm not going to force, you know, of course, even if we know which is best for which people, I would be totally against that. I'm more for freedom of choice than probably anybody, almost anybody I know, when it comes to education. But this is not the way we could ever find out if it works. All right? So subjects will be happy. Right? But what happens? The treatment and control could be very different. Because the people who might want to take it in one group, in person or online, are different types of people. And some of those ways they're different could affect the results, could influence our results. Okay. Now, so how about give the drug to those students most likely to benefit from it and give the rest a fake drug. That way, okay, everybody thinks they've taken the drug. This placebo, you probably all know, just means making the two groups, the treatment, indistinguishable so that the two groups are more alike. By giving, with medicine, they always give the control group a fake pill. So it's a fake treatment. So we could do that with the drug here. So then nobody knows which they're getting, and then I decide who I think would benefit. But the whole reason I'm doing this study is because I don't know who would benefit. It defeats the whole purpose. It kind of makes no sense at all. Because, you know, we're trying to test to see if the drug works. We don't know which group it would benefit, right? So this is really, and it's necessarily going to make the two groups different. So this makes no sense. Because we're doing the study to find out which is better. We don't know. And it'll just mix things up. If we make that, we're ruining the design. We're defeating our goal. We're choosing to make the two groups different, which is crazy. All right? We're choosing. So this is really stupid. Choosing to make two groups different. It's choosing to make treatment and control different. By the way, can you read my handwriting in the back row? Raise your hand if you're having problems. All right, sir, you come on up front. Good job. And anybody should feel free to move so they can see better. All right, next one. All right, match the two groups on all relevant characteristics. So, you know, whatever we think might affect how you're going to do at the end. ACT scores, your major, your math background, maybe we want the same number of males and females in both groups, so proportionately the same, etc. Now this sounds really good, right? What would be the problem with this? It sounds great, because why not use our knowledge of what could affect the outcome and try to match the groups up? Well, there's a number of reasons, but before I even just start, I'm going to try this thing. Do we have time? Yeah, probably. Okay, so I'm just going to do this quick experiment. And so when you see these numbers on the screen, just pick one randomly. Just like randomly pick a number. Okay, just do that. All right, and I'll just put it up there. You all got your number? Okay. So how many people chose the number 1? Raise your hand. I mean, come on. I hope you all chose. Did you all choose a number? Okay, how many people chose the number 1? Okay, I got to show this to the at-home audience. No one has their hand raised. I mean, is that even clear? This is so funny. Let's see if we can. Sorry, guys, you're on. Nobody can recognize you, but nobody has a raised hand. Okay. All right, now we got to redo this. All right, now, how many people? Let's just see. So we just put this here. We'll put it here. 1, 2, 3, 4. And no one chose this. Okay, how about 3? Raise your hand. Oh yeah, let's just show everybody I'm not lying here. They say statistics lies. Raise your hands high so you can see. Wave them around so they look like things are happening there. Can you see? Wave them. Can you see it? This is not working. But there are lots of people. What would you say? About half the people raise their hand or more? Do it again. I want to see. Oh, yeah. I'd say about 70%. Okay, so approximately 70%. Sorry. This is so cool. And it doesn't usually work out with no one here. Now, how about 2? I'm just curious. 2 is one. Looks like about 20%. How about this one? Looks like about 10%. So this is approximately 20%. I didn't do it exactly. We could have done with iClickers, but we're not using iClickers, by the way. All right. So about 20%. And now, this was random. And did you know that you're biased against 1? That's the whole point. The people, did you know you're really pro 3? No. I mean, what I'm saying is that when people, this really illustrates something that's very important to statistics, 2 things. One, that humans always have bias. What do I mean by that? I don't just mean racial, sexual bias that we all are aware of. I mean systematic preferences. We are hardwired to have systematic, automatic, unconscious preferences. Otherwise, we wouldn't survive on this planet. We react without knowing how we're going to react or why we react or not even aware of it. So whenever you have humans deciding anything, you're going to introduce bias in the sense of systematic bias. That's one thing that I wanted to illustrate. And I should probably write that down now before I forget what I said. So anytime, oh, now I have a different pen. Okay, so I'll use this one. Anytime humans choose to introduce systematic preferences, systematic differences, which is called bias. Now, let's not throw the baby out with the bathwater. This is a good first step, and I'll explain in a minute. But first, it's a good first step. All right? We're gonna do some of this, all right? And we'll talk about that in a minute. But I want to talk about the second reason why I love this example is because it not only highlights that we have systematic preferences, but it also highlights what we mean by random in stats as opposed to the word random in everyday life. I said randomly choose 1. You're all fine with that because what we mean in everyday life is usually just some haphazard thing, right? That's what we mean by random, haphazard procedure. In statistics, we mean a very planned introduction of chance. And there's lots of different ways you could do this. In this case, if we wanted an even distribution among these, then we'd introduce, we'd make sure that each number had an equal chance of being chosen by, having each person have a spinner, 1, 2, 3, 4, just spin the numbers or spin the spinner and with equal chance of it landing on either one. So we'd get 25%, 25%, 25%, 25%. And then we can use the laws of chance that say that in the long run, certainly not with like 5 people, but in the long run, you're going to get very close to 25%, 25%, 25%, and 25%. And that is why randomization is by far the best way to ensure that the treatment and control groups are alike. And not only on the characteristics you can identify that might be relevant, but on all the characteristics. All right? So this is good as a first step, but your last step, your final assignment, but the final assignment to treatment and control should be random. And this is called blocking, which we're going to get to on the next page. But final assignment to treatment and control should be random. That's very important. Okay, so now why do we want, so this is best. These are all, those are all, sorry, I'm jumping around here. These are all non-random. And this one is the best. Random is the best. Why? Why is random the best? Because it eliminates systematic differences. It eliminates bias. And what we mean by that is systematic preferences. Systematic differences between treatment and control. You'll still have accidental differences, right? But not systematic ones. So eliminates bias, systematic. So accidental differences remain. What I mean by that is that even if you each had a spinner at your desk and we're not going to get exactly 25% of the class picking each one, but the larger the class is, the closer we'll get to that. So accidental differences remain, but average out as your sample increases with enough subjects. All right, so this is really difficult to do, but it's the ideal. So now, getting back to this idea, this is good as a first step to match the two groups. Let's think about why, especially in small groups. It's called blocking. Okay, so that's what we're going to look at now. So, random assignment to treatment and control works best to make the treatment and control groups as alike as possible because it eliminates systematic differences, which we call bias. So with enough subjects, random differences average out. But when you have a small study, they don't average out. So it's very important to block first. So with small sample sizes, researchers block subjects into relatively homogeneous groups first, and then flip a coin to decide who gets which treatment within each group. That reduces accidental differences that could be a problem. So here's what I mean. Suppose there were only 36 students in the class, and 18 of them have A averages in previous math classes, and 18 of them have B averages in previous math classes. With only 36 students, random differences in assignment into the drug, into the this is the treatment group and the control group, could result in large accidental differences. So let's just think about it. So if we didn't block, okay, here let's say there was a class that had 36 students, 18 of them had A's and 18 of them had B's, right? And if we just shuffled this all up, mixed it all up, and took half of them and put them in the treatment group, the drug group, and put the other half in the placebo group, right? We could get a very uneven distribution here, right? So this would be a problem because why? Let's say this is before we even gave them the drug, before we even gave them the drug. We're already starting out with the scales tipped in favor of this treatment group, right? Aren't we? Because aren't they likely to do better at the end? So this ruins our experiment, even though we did random assignment, because we have big accident. You know, if you flip a coin, only 10 times, you're not going to get close to 50%. You're not likely to get, you could easily get 70% heads and 30% tails, right? But if you did it 100 times, you'll get much closer to 50-50. So with this small sample, it's a problem. Now, what do? So we block. And what does that mean? It means you put all the A's in 118 here and all the B's here. Now what do? So this is, you think that this is a relevant characteristic, so you're separating them, right? Then what you do is you take half of these 18 A's and randomly put half in the treatment group, 9 of them here, and the other half randomly, this is random, to the control group. We haven't introduced any bias at all, right? We're just making sure, and do the same with the B's, we're just making sure that our final assignment isn't different here. This is going to really affect things. So it doesn't, it just reduces the chance variation. It doesn't without introducing any bias, and it's ideal to do no matter how big your group is. This is if you ever look at any studies, they'll say they blocked on something they think is really important, even if it's a large study, because it will always help. It just doesn't matter as much with large studies. But if you come across something that you think is really important and you want it to be exactly evenly divided, well, this is how you do it. Okay? Does that make sense? All right. So why would this be a problem if, well, we just said why this would be a problem. The treatment and control group would be different if we didn't block. We wouldn't be able to tell, you know, whether the group with the 13 A's did better because they had more A's to begin with, or did better because they had the drug. I'll write that down because that's super important. We wouldn't be able to tell whether the group with more A's because it had more A's to begin with, or because of after when we measured the responses, we wouldn't be able to tell whether it was better because it had more A's to begin with, or because it was given the drug. All right, I think you got that. What's the other thing? Can you find a way to ensure the same proportion? Yes, blocking, see below, that's what we just did. Could this introduce bias? No. Just couldn't. Can't. I mean, however you divide, let's say your division was all wrong. Let's say you got it all mixed up. It wouldn't matter. You're still randomly dividing. You'd be no worse off than you were to begin with. Is it always better to block first? Yes. But it doesn't really matter as much with large samples, but it's less necessary with large samples because this is just a control for accidental differences, and they average out with large samples. Okay, I think you've got the idea. So this, let's just write this. This will make the two groups as alike as possible. Okay, so if you have a small sample, block. And I think we'll say that on the next page. Let's look. Maybe it doesn't. Okay, let's write it here. So if you have a small sample, just so you remember it. If you have a small sample, oh, how do I turn this off? Sorry, excuse me for that. If you have a small sample, and you think a variable could, you need to block. If you have a small sample, block. All right, on the variable you think might influence the results. All right, now, let's see. I want to get to chapter 2. So let's just see what else we have to cover here. Okay, so random assignment is key. As long as you have enough subjects, Flipping a coin to decide whose treatment and whose control is ideal. Why? It eliminates human bias. We saw that. And there's another reason, because random controls are based on chance procedures. And without a chance process, we can't use a lot of our statistical methods to analyze whether the treatment really worked. Okay, what do I mean by that? This is a preview into, this is a preview. We'll study this more. We'll study this in parts 6 on significance tests and p-values. But let me just give you a preview while we're here so you understand what we're talking about. All right, so what I'm talking about is this. Let's say you see some difference at the end of the study. Let's say it's the end and we've all done this and you all have your scores. And there is some difference between the treatment and control group. Let's say the control group, got an 88 and the treatment group got a 90. That's a 2-point difference. Can you conclude from that that the treatment worked? I mean, if the difference was like 60% versus 90%, of course you're going to say it worked. But basically, how big a difference do you need before you can say it worked? The reason I'm saying, imagine, the way we can think about this is, imagine if both of them were placebos. Imagine if the drug was a complete dud. It was no better than the placebo. Then it would be equivalent to just randomly taking all your scores at the end, as if nobody had any treatment, taking all your scores at the end, and randomly dividing them into 2 groups. Would those 2 groups really be exactly the same? Exactly the same to how many ever decimal points? No, there's always going to be a difference just due to randomization, right? You're not going to get exactly the same scores in the 2 groups because it's due to random chance. In fact, it's just as, one possibility is that, let's say you had 100 people, the 50 highest scores could end up in one group and the 50 lowest in another. That's as likely as any single possibility. It's just one way that could happen. So, it's just the laws of probability govern that. So what we're going to do with these significance tests and later on what a lot of statistical procedures do is they assume the null hypothesis, that nothing went on, just what we said. And we said if the drug didn't work, if it was just a complete dud, how likely would it be to get this big a difference just by the luck of the draw? So we'll compute that. That's easy to do. We'll say, okay, let's say there's a 2-point difference. And it's intuitively it doesn't coincide with your intuition very much. People are notoriously terrible at making these intuitive probabilistic calculations. And so so we're just going to learn methods to do that. That's a huge part of all statistics, is identifying an underlying probability model and calculating the chance that it would have happened just by the luck of the draw. And if that chance is too small, then we're going to say that it would have happened, that if there's too big a difference to have happened by the luck of the draw, the possibility is too small, like there's only a 1% chance that could happen, then we'll reject that null and we'll say the result was significant. They're significantly different. So that's, whereas if there wasn't some underlying probability model, then when they're different, we can't assess the likelihood of. We can just say, yeah, they're different, but we can't assess the likelihood that would have happened, just by the luck of the draw. So that's what we're going to do. So that's the idea. But that's to come. All right, so then there's 2 other things that you've probably heard of about, one is to make the ideal experimental design. When possible, remember the goal, treatment and control as alike as possible. That's the goal. So if possible, we want to eliminate the psychological effect of thinking you had a treatment by making everyone think they had the treatment by introducing a placebo. That's not possible in many situations, but when you have a drug, it is. So that's important to do. And also, it's important, that's called single blind, if you do that. And then double blind would be that if the person who's conducting the study doesn't know who got which treatment, because that could bias the results too. I mean, if I knew which person got the drug, I'd probably be more interested in their results, might call on them more, might, you know, so what happens is the person, the evaluator is blind, and at the end, you know, the one who measures the responses is blind, doesn't know who's in which group, and then at the end the blind is broken. So that's the ideal experiment. All right? And that's what's called the gold standard, the randomized controlled double-blind experiment. And, but the randomization is the real key part, because lots of times the blinding can't be done. Like with an educational method, you know which group you're in. You know if you're online or in person. Understand? All right. Now, do we have time to do this? How many minutes do we have left? Only 12, right? Darn, I wanted to start this. But do you mind if we just keep going? You can even, like, I just wanted to, I know you mind, but I'm going to make you keep going a little bit longer, okay? I want to get to this so you can do the homework. The homework's posted. At least you'll know something about what this is. All right, now we're going to talk about something super important. Observational studies and confounders. We're going to spend, this is a key part of the course. Okay, so the main problem with these observational studies is when the subjects themselves choose the groups, there's bound to be lots of differences between them, between the two groups. That's bad. And those differences mix up our study, right? You can't tell if it was those differences that might influence the results or the treatment that did. So what do we do? Observational study can show that there's an association between two things, but you can't tell if it was the treatment causing the response. You can't conclude causation. And we all want to know causes. We want reasons. We all believe, you know, there's some reason. That's, I don't know anybody who doesn't want to find a reason, because if you found the cause, you can change things. And we all want to have that control. So observational studies can show association, but not causation. So the key question that you're always faced is, if you see some difference between the treatment and the control at the end of the study, is, was it the treatment that truly caused it? Was there something about the treatment, that happens first, that caused, we call it causal link, that caused the response? If so, well, great, then we've discovered something. You know, give them the treatment or don't. If it's a positive thing, give the people the treatment. If it's a negative thing, don't. We can affect, you know, but we might see a different, we might be in this situation where we see a difference between the responses, but these two, like the treatment group might have has a different response, but we don't know if it was because those two groups were different to begin with, because they chose themselves. Like maybe the in-person class has higher scores, or the online people are higher scores, whatever. They're different to begin with, or so that is affecting whether they're going to treat to the in-person or the online, which would be the treatment, and also affecting their response, or whether it was, so we don't know which way the arrows go. We don't know if this confounds and mixes up things and makes it so eliminating this wouldn't do anything to our response, because there's a confounding factor, a lurking variable. Okay? So that is the idea. It's a difference. This confounder, let's just write this down, and it's not a co-founder, it's a confounder. People say co-founders all the time. It's a confounder. And what is it? It's a difference between the treatment and control groups that mixes up, that confounds. Confounds means mix up, confuses. I'll use that. That confuses. Confounder is a confuser. That confuses our results. Confuser. That's what it is. It makes things super confusing. What's going on here? We can't conclude anything. We just know two things are associated. When we're really, what we're usually looking for is this causal link. Cause, not casual, right? Cause, because, a cause. Did the response happen because of the treatment? This is a cause, not a casual thing. This is a cause link. I'll just call it a causation link. Maybe you'll remember that way. A causation link instead of a, because people always say causal. I know, I can't get rid of that. So maybe think of it as a causation link. So it explains why, how, or why the treatment causes the response. How or why, I should say. How or why the treatment causes the response. And how are we going to figure that out, which of those two it is? We're going to do that by stratification. What are we going to do? We're going to try to figure out what could be a possible confounder and then block on that. So it's like blocking after the results are in rather than before, like you do in a randomized study. So it's okay, we're going to figure out what could possibly be the confounder and then block on that, like put all the, say if it was A students, then we'll compare A students in the in-class to the people who had prior A's to A students in the online, right? And we'll do the same with the B students. So it's, so basically it's just like blocking, but its blocking is done before a randomized experiment to make the two groups we're comparing more alike, to get rid of those accidental differences. And stratification, we can't do anything before because we're not making the assignment. All we can do is look at the results. So stratification is done after an observational study. Basically, you want to compare apples to apples in the two groups, right? So you block or stratify to make the two groups that you're comparing as alike as possible. So just to continue with our example, we do the same. Here's the differences. Like if we did stratification, back to the same example. I like to do this a lot. Just keep everything the same and change one little bit. And so you can see, make it clear what the difference is. So suppose the 36 students were allowed to choose themselves instead of random assignment to take the drug or not. And let's say this is how they chose. The students chose. There was no randomization here, and they ended up very different. So they had, these are these systematic differences that result because people choose. Now what are we going to do with that? We can't rearrange the groups now, but what we can do is stratify. So we would compare. This is, see the stratification here, layers. So we know this is going to be critical variable in influencing the responses that we're measuring later on. So we compare them separately, stratified into layers. And here we compare the 13 A's to the 5 A's. Well, is that a problem that there's different numbers here? No, because we're going to compare the average score of these 5 A's compared to the average of these 13, right? So we're just going to take, so it doesn't matter that there's more people in this group than this group in terms of, more people isn't going to give them a higher score. We're comparing averages here and averages here. So that is the idea. The problem with this is that lots of times there's more than one variable. So let's say we thought income was a confounder because high income students might be more likely to choose one or the other. And so we'd have to, let's say, what would we do then? We'd need to block on income. So we'd have to break these two subgroups in each, these, into 3 more groups like this. High income, middle income, and low income. And then you'd have high, middle, and low. And you'd have to do the same here. This is crazy. High, middle, and low. And look what happens if you do that. You end up with so many groups, middle and low, that you need a bigger sample size. Like with these 5 people, we might get 0 people in one of these groups. So what do we do instead? And this is just a preview into what we need to break. Okay, let's say, okay, we wouldn't have enough people to do that, enough samples. So one way to deal with that is modeling. And we're going to talk about this modeling later on in chapter 30. This is basically creating models where we include these, what we think could be confounders, as covariates or as variables in a linear model, in a regression model, as another variable, a predictor variable. So one way to do this, and we're going to look at this in chapter 30. All right, so that's, what did I do? That's the beginning of it. So we'll start with page 7 next time.